This function is a polynomial, 34x squared minus 24xy plus 41y squared. But exactly what kind of function is it? For instance, is it ever negative? What is the shape of its graph? Now, if I told you to make the following change of variables from x and y to u and v, then you'd find that the expression reduces to 25u squared plus 50v squared. Then suddenly there's a lot we understand about this function. It's now obvious that this function is never negative, since squares are never negative. Moreover, the function is only 0 when u and v are 0, and that only happens when x and y are both 0, because, as you can check, the linear change of variables is invertible. These things were not obvious from the polynomial in x and y. You see, here is hidden structure that has now been revealed. How did I find it? Let's develop some theory first. We've been speaking a lot about linear transformations and the matrices that represent them. Here's a picture of a linear transformation on the plane. We've seen in prior lectures that they map parallelograms to parallelograms. While they preserve parallel lines, they don't preserve angles, nor do they preserve distances between points. So they can warp space and change volumes. In fact, we've seen that the determinant of a matrix tells us the scaling factor by which volumes get changed by the associated linear transformation. It would be nice if we could rely on linear transformations that do not change volumes or angles or distances. But this leads us to ask the question, what are the linear transformations which do preserve angles and volumes and distances between points? For instance, in R3, rotations around the origin don't change volumes, and they do preserve angles and distances. Are there others? Such linear transformations have a special name. They're called orthogonal. Let's see if we can figure out exactly which linear transformations those are, and then see some applications. Recall that the standard basis vectors are pairwise perpendicular and length 1. So if the columns of a matrix tell us where the standard basis vectors get sent by the associated linear transformation, then if the transformation preserves angles and lengths, we should expect the columns of the matrix to remain pairwise perpendicular. And we expect those vectors to be length 1 as well. Let's make a definition. We will call a set of non-zero vectors orthogonal if all pairs of vectors in the set are perpendicular. Or said another way, if the vectors are v1 through vn, then for all pairs I and j, where I is not j, the dot product of vi and vj equals 0. Recall that the dot product of two non-zero vectors is 0 if and only if the two vectors are perpendicular. While the words orthogonal and perpendicular are synonyms, we usually use the word perpendicular for a pair of vectors, whereas the word orthogonal applies to a set. We often use orthogonal sets as reference frames to measure other things by. In particular, it's nice when we have a basis that's orthogonal. And you'll see later, it's even more convenient when the vectors have length 1. In that case, we call the set of vectors orthonormal. By the way, I should say the word normal is so overused in mathematics. In this context, normal refers to length 1, so to normalize a vector means to scale it so that it's length 1. So an orthogonal set can be turned into an orthonormal set by simply normalizing each vector. An orthogonal set might look something like this set of vectors in R3. Each vector is at right angles to all the others. And if they were all length 1, they would be an orthonormal set. What else should we expect of an orthogonal set? Well, since all the vectors are pairwise perpendicular, we might expect the set to be linearly independent, and that's indeed the case. The theorem says an orthogonal set is linearly independent. We can prove this pretty easily by appealing to definitions. If V1 through Vn is an orthogonal set, we'll show that if the linear combination C1V1 plus CnVn equals the zero vector, then each of the coefficients Ci is equal to 0. The way to see this is to consider the linear combination C1V1 through CnVn and take its dot product with the vector Vi. If you do this and you look at it two different ways, you'll see something interesting. On one hand, this dot product must be 0 because we assumed the linear combination C1V1 through CnVn equaled the zero vector. On the other hand, if you distribute the dot product, all the terms vanish because Vi and Vj are perpendicular. The only term that survives is the term Ci times Vi dot Vi. So if the whole dot product is 0, this term must be 0 as well. And since Vi is not the zero vector, Vi dot Vi is the square of the magnitude of Vi, so the coefficient Ci must be 0. This argument holds for every I, so we have shown what we promised to show. Let's look at some examples. Here are three vectors: a unit vector pointing in the x direction, one of length 3 pointing in the y direction, and one of length 2 pointing in the z direction. Intuitively, you know these are orthogonal. And of course, you can verify that the dot product of any pair of them is 0. Here's another set of vectors. This set is not orthogonal. It's not easy to visualize, but it's easy to check the dot products are not all 0. In fact, if you just take the dot product of the first two vectors, you get 2, which means the first two vectors are not perpendicular, so the set can't be orthogonal. Now look at this set of vectors. Though this set is hard to visualize, you can check all pairs do have dot product 0. So the set is an orthogonal set. If we wanted to make this an orthonormal set, we could divide each vector by its length to make them all length 1. Now consider this set of 3 vectors in R4. You can check that this set is orthogonal by checking the dot product of each pair is 0. Since it's a linearly independent set, it must span a 3-dimensional subspace of R4. And if you want this set to be orthonormal, you can divide each vector by its length. A natural question is, given a vector in a subspace S, how can it be expressed as a linear combination in a given basis for that subspace? Normally, you'd have to solve a system of equations to find the coefficients for this combination. But if the basis is orthogonal, then finding the coefficients is easy. If the orthogonal basis is V1 through Vk, and we want W to equal a linear combination C1V1 through CkVk, we can just write Ci equals W dot Vi divided by Vi dot Vi. This is the coefficient for the component of W in the Vi direction. The intuition behind this is that if you project the vector W in the Vi direction, you get a vector whose magnitude is the length of W times the cosine of the angle in between, which by the geometric definition of the dot product is just W dot Vi divided by the length of Vi. And this vector points in the direction of the unit vector Vi divided by the length of Vi. So, the vector is the product of this magnitude times the unit direction. That's W dot Vi times the vector Vi divided by the square of the length Vi. This is the vector Vi times a coefficient, W dot Vi divided by vi dot vi, as we claimed. The representation of W in terms of the VI is unique because if you take the dot product with VI, all the terms vanish by orthogonality except the ith term, so that W dot VI is indeed Ci times Vi dot Vi. Division then shows Ci equals W dot Vi divided by Vi dot Vi, as we claimed. And if the set of vectors is orthonormal, then this representation is even easier, because then the denominator of this fraction is just 1. So if Q1 through Qk is an orthonormal basis for some subspace S, and W is chosen from S, then W is a linear combination of the Qi's with each coefficient just W dot Qi, and this representation is unique. This is why we like an orthonormal basis. We can figure out the coordinates in this basis just by doing dot products. Now, if you put the orthonormal basis as columns of a matrix Q, then Q transpose times Q must be the n by n identity matrix. This is because the ijth entry of Q transpose Q is just the ith row of Q transpose dotted with the jth column of Q. This dot product is 1 whenever I equals j, and it's 0 otherwise. Let's look at this example. For this 2 by 2 matrix Q, you can confirm that both columns have length 1, and if you dot them, you get 0. So the columns are an orthonormal set. Then Q transpose switches the rows and the columns. Now you can verify that every entry of the product Q transpose Q is just doing a product of a row of Q transpose with a column of Q, and thus it gives the identity matrix. So then Q transpose is just Q inverse. If Q is square, meaning the number of elements of the orthonormal set is equal to n, the dimension of the vectors, then the orthonormal set spans all of Rn, and we call Q an orthogonal matrix. This is a strange name because you might think we should call such a matrix orthonormal, but this is the convention that has historically been used, so we'll stick with this odd choice of name. So just remember that an orthogonal matrix has orthonormal columns and is square. For an orthogonal matrix, taking the inverse is very easy, because as we saw, Q inverse is just Q transpose. A good example of an orthogonal matrix is a rotation matrix. You can check that Q transpose times Q is just the identity matrix. But intuitively, it should make sense the matrix is orthogonal because our motivation for orthogonal matrices was looking for linear transformations that preserve angles and volumes and distances between points, and rotations do that. Another example of an orthogonal matrix is just the identity matrix. But since the order of the columns shouldn't matter, then any permutation of the columns of the identity matrix should be orthogonal as well. Such a matrix is called a permutation matrix, and its actions on Rn just swap the roles of the axes in n-dimensional space. So now let's list some properties of orthogonal matrices that will be useful for us to note. Let Q be an n by n orthogonal matrix. Then the first property to notice is Qx dot Qy is just x dot y for any pair of vectors x and y in Rn. This follows because Qx dot Qy is, as matrices, just Qx transpose times Qy, which is x transpose times Q transpose times Q times y. Since Q transpose times Q is the identity, this product is just x dot y as desired. We can summarize this property by saying that an orthogonal transformation preserves dot products, and therefore also angles. The second property to note is that orthogonal matrices preserve lengths, so that the length of Qx equals the length of x for any vector x in Rn. This follows from noticing the length of Qx is just the square root of Qx dotted with Qx, which is the square root of x dot x using the first property. And that is just the length of x. By the way, when a transformation preserves lengths, we call it a special name. We say it's an isometry, which makes sense because the root iso means equal and metry refers to lengths. Each of these first two properties is in fact equivalent to Q being orthogonal. That is, property 1 implies the matrix Q is orthogonal, and property 2 implies the matrix Q is orthogonal. I'll leave these as exercises for you to show. Another property of an orthogonal matrix is that the rows form an orthonormal set like the columns do. This is because the rows of Q are columns of Q transpose. And we already know that Q transpose inverts Q. So Q transpose is the identity matrix, which is the same as saying Q transpose transpose times Q transpose is the identity matrix. That shows Q transpose is orthogonal. This also establishes a fourth property, that Q inverse is an orthogonal matrix because Q inverse is Q transpose. A fifth property, which won't be a surprise if you think about what orthogonal matrices do to volumes, is that the determinant of an orthogonal matrix Q is plus or minus 1. This follows from noting that Q transpose times Q is the identity. So the determinant of Q transpose times the determinant of Q must be 1. But the determinant of Q transpose is, if you recall, just the same as the determinant of Q. So this means the determinant of Q squared is 1. And that means the determinant of Q has to be plus or minus 1. If determinant of Q is minus 1, then the negative determinant is a clue that the action of Q does some kind of reflection without changing distances or angles. A sixth property of an orthogonal matrix Q is that if lambda is an eigenvalue of Q, whether real or complex, the absolute value of lambda is 1. You can see this from the eigenvalue property QV equals lambda V for some non-zero eigenvector V. Taking lengths, we see that the length of V equals the length of QV by property 2, and that is the length of lambda V, which is the length of lambda times the length of V. And taken together, this means the length of lambda must be 1. So the eigenvalues of an orthogonal matrix must lie on the unit circle in the complex plane. A seventh property is that if Q1 and Q2 are both orthogonal matrices, then their product Q1 times Q2 is. And that can be seen in a number of ways. And again, I'll leave it as an exercise for you to see why. Taken together, these properties should give you a pretty good feel for how orthogonal matrices behave. Because they preserve dot products and lengths, they basically behave like rigid motions, possibly together with a reflection of n-dimensional space. And there'll be reflections if the determinant is minus 1. We like orthonormal bases because, as we've seen, they can be good bases to represent vectors in. We'll now show you how you can take any basis of vectors for a subspace and turn them into a basis that's orthonormal. Given V1 through Vn, a basis for a subspace S, we construct a new orthogonal basis by sequentially modifying each Vi to form a new vector, Wi, in such a way that the Wi are length 1 and perpendicular to all the W vectors before it. The first step is just to take W1 to be V1. Then we take W2 to be V2, except that we'll subtract off the component of V2 in the W1 direction. This means subtracting off the W1 vector times the fraction V2 dot W1 divided by W1 dot W1. So you can check now that W2 is perpendicular to W1. You should stop the video right now and actually check this. Next, we'll continue in this fashion with W3. We'll start by modifying V3 by subtracting off the components of V3 in the W1 and W2 directions. You'll get an expression like this one. And I encourage you to check that W3 is in fact perpendicular to both W1 and W2. If you keep doing this process sequentially, you will get an orthogonal set. Then you can normalize each vector Wi by dividing by its length to get a unit vector Q sub I. Then you will have an orthonormal basis Q1 through Qn. In our construction, you can see that at every step, we've constructed the first k vectors of our orthonormal basis to have the same span as the first k vectors v1 through vk. This process that we've just done is called the Gram-Schmidt process. And what we've just seen will help us see something called the QR factorization of a matrix. It turns out that any m by n matrix A with linearly independent columns has a special factorization into the product of Q and R, where Q is m by n with orthonormal columns, and R is an n by n invertible upper triangular matrix. We'll first explain how to find such a factorization and then do an example. To find Q, we can use the Gram-Schmidt process on the columns of A. Since they are linearly independent, Gram-Schmidt will work. And if you let R equal Q transpose times A, then you will see that Q times R is Q times Q transpose times A, which is just the identity times A, which is A. The matrix R obtained in this way must be upper triangular, because if you look at how Gram-Schmidt works, then V1 can be expressed entirely in terms of Q1, V2 can be expressed entirely in terms of Q1 and Q2, and in general, Vk can be expressed entirely in terms of the vectors Q1 through Qk. The diagonal elements of R must all be non-zero because we constructed Qk as a normalized version of Wk, and Wk was defined in terms of Vk and W1 through W sub k minus 1. So the coefficient R sub kk must be non-zero. And by the way, it is known that if you require the diagonal elements of R to be positive, then the QR factorization is unique. Let's see some examples. Here is a matrix with linearly independent columns. You can check that the columns, however, are not orthogonal. Now let's label the columns V1, V2, V3. The Gram-Schmidt process says to start with W1 equal to V1, which is 1, 1, 0, 0. The length of this vector is the square root of 2. We could use this length to normalize the vector now, but to make calculations easier to see, we could also just wait to the end, but we'll record the lengths now for future reference. We'll set W2 to be V2 minus the component of V2 in the W1 direction. So V2 is the vector 0, 1, 1, 0. And we are subtracting off some multiple of the vector 1, 1, 0, 0, which is W1. Which multiple? Well, it's just V2 dot W1 divided by W1 dot W1. You can check this is just 1/2. So you get W2 equals minus 1/2, 1/2, 1, 0. You can check this vector has length square root of 3/2. Similarly, we can compute W3 as V3 minus the components of V3 in the W1 and W2 directions. This is 0, 0, 1, 1 minus 2 terms. The first term, as it turns out, is 0 over 2 times W1, which comes from the fact that W1 is actually already orthogonal to V3. So there is no component of V3 in the W1 direction. The second term is 1 over 1.5 times the vector W2. You'll find that W3 is 1/3 minus 1/3, 1/3, 1. And it has length the square root of 4/3. So now if we normalize W1, W2, and W3 and put them in the columns of a matrix, we get this matrix Q, which has orthonormal columns. To find R, we can look at Q transpose times the original matrix. If you do that, you find R to be this matrix. And now you can check that Q times R actually gives back the original matrix. Now, the reason we like factorizations is that they tell us something about the structure of a matrix transformation. The matrix R here is basically playing the role of Gram-Schmidt in taking a set of linearly independent vectors and squaring it up and scaling each dimension to form vectors that are orthonormal. This insight can be useful in applications, and we'll see one in a later lecture on statistics. Let's close by discussing another application of orthogonal matrices. Recall that a square matrix A is diagonalizable if A equals P D P inverse, where P is invertible and D is diagonal. We've seen that P's columns must then be eigenvectors of A, and the diagonal elements of D must be associated eigenvalues in the same order. We've discussed the idea that one way to think about the action of P is that it's like changing bases from the standard basis to some other basis. But sometimes that change of basis can be done nicely by an orthogonal matrix. Recall that for orthogonal matrices, the columns are an orthonormal set, and the inverse is the transpose. So let's define a stronger concept. We'll say a matrix A is orthogonally diagonalizable. That's a mouthful, isn't it? If, in addition, P is required to be orthogonal, so that A equals PD P transpose. It turns out something special called the spectral theorem guarantees that orthogonally diagonalizable matrices are precisely the same as the symmetric matrices. Remember, a symmetric matrix means A equals A transpose. Or what's the same, the entries are symmetric when reflected around the main diagonal. So the spectral theorem says a matrix is orthogonally diagonalizable if and only if it is real and symmetric. We'll just prove the forward direction of this if and only statement. We'll show that orthogonally diagonalizable matrices are symmetric. The proof goes like this. If A is orthogonally diagonalizable, then A equals PDP transpose. Then A transpose is the product of the transposes in the reverse order, which is P transpose transpose, D transpose, P transpose, which is just P, D, P transpose. But then this shows that A equals A transpose. So A is symmetric, as we desired to show. Okay, now let's recall the polynomial in xy we started the lecture with, which, by a clever change of variable, I made a simple function of u and v. How did I do this? Well, the first thing to realize is that the polynomial in x and y can be represented as a matrix product. of the vector xy transpose times the matrix A times the vector xy. And such a form is called a quadratic form. For such forms, the matrix A can always be chosen to be symmetric because the symmetric terms of the matrix contribute to the same term in the quadratic form. And because a matrix is symmetric, it is orthogonally diagonalizable by the spectral theorem. That suggests I'm going to be able to simplify the polynomial if I look at it the right way. So let me replace A in the quadratic form by QD transpose, where Q has eigenvectors of A in its columns and D is diagonal. Now notice that if I let the vector UV be Q transpose times the vector XY, the expression simplifies greatly. I get a quadratic form in U and V with a diagonal matrix in the middle. The fact that it's diagonal means the polynomial won't have any mixed terms in U and V. The fact that the diagonal entries are eigenvalues, and in this case they are 25 and 50, and they're both positive, means the coefficients of U squared and V squared are going to be positive. So we can tell whether a form is going to be non-negative by looking at the eigenvalues of the matrix A. And the fact that Q is an orthogonal matrix means that this change of variables does not warp the plane at all. So whatever geometric features the UV polynomial has, the XY polynomial also has, just rotated. For instance, the level sets of the UV function are ellipses with major and minor axes along the UV axes. But then the level sets for the XY function are ellipses too, just rotated by an orthogonal transformation. The theme of hidden structure again shows itself. It was not clear at all that a quadratic function should have any linear structure. But the other thing we've been stressing is that linear structures are everywhere.